Alright guys, so now I'm going to solve this thing here. Okay. Now you want to find the centroid of this region here. This region, okay. So what are you going to do? Well, you're going to divide this region. We're not going to use calculus because this region, everything is squared or rectangular. There are no curves like this, so you don't have to use calculus. You could if you wanted to, but there's no need. So in order to find the centroid point, the coordinate, we're going to have to consider this point right here. This point is going to be 0, 0. Okay? That's going to be that point. And what we're going to do is divide this stuff into many regions, each one with its respective centroid. And then we're going to use the weight of that region and at that point of the centroid to find out the centroid of the entire figure. Okay, so what we're going to do is divide this thing like that here. We're also going to divide it here. All right, and now we're going to find the coordinates of these centroids in here. And I'm going to say A, one's going to be B, and this one here is going to be C. Okay. So what is, for example, the mass of the region A? The mass of A, you see, we're going to consider the entire figure having a density of 1. Okay. So, and it's going to be uniform density. Everywhere is going to be 1. So because the density is the same and it's just 1, and it's a density per area. It's not a mass per volume. Okay, we're talking about that laminar density, which is mass divided by area. We're going to consider this to be 1. Okay, so the mass divided by area, the mass is going to be the area. It's directly proportional to the area. And so what is the area of A? Well, 1 times 2, okay, so it's 2. The mass, I'm going to erase this thing here. The centroid of A, where is it going to be? The coordinate. The coordinate is going to be, where is it? It's half and 1, right? Or because it's, oh no, hold on. Talking about 1 plus 2, so it's 3. It's 3 here. Yeah, the height is 3. So it's 1 times 3, 3. The centroid is going to be half and 1.5. So the centroid will be here. All right. Mass of B is going to be equal to, well, it's 3 times 1. So it's also going to be 3. The centroid of B is, oh, this is 1. Okay. So this is another 1. You could say that it's 2.5. Yeah, it's 2 in here. And you kind of gotta, how can I say this? This is 1 and this is 3. So the half of this is 1.5. So it's gonna be 1 plus 1.5, 2.5. So it's like that. Okay. And the y is going to be just half. The mass of C is going to be equal to 2 times 2 is 4. And the centroid of C equals, well, in the x direction, you got 1 plus 3, 4, plus half of 2, which is 1, 5, right? Yeah. 5. And the height is going to be 1. So if you want to find the centroid now, all you got to do is to do these things, right? The moment about the x is going to be the mass times the y, right? So it'll be 9/2 plus 3 times 3/2 plus 4. Now I'm going to put a 2 here, and here's going to be an 8. So it'll be 12 and 8, 20 divided by 2, 10. And the entire mass, 3 plus 3, 6 plus 4, 10. So the mass is equal to 10. So y bar is going to be, well, let me just find, I'm already on a roll, so the centroid about y, okay? So it's going to be the mass times the centroid x coordinate. 3 times half, it'll be 3/2 plus 3 times 5 divided by 2, 15 divided by 2, plus 4 times 5 is 20, but divided by 2 is 40, right? So this is 1858. Is that it? Yeah, 1858 divided by 229. All right. So the x bar equals my divided by m, which is the same as 29 divided by 10. All right. Let me just think about one thing here. Okay. Y bar will be the moment about the x-axis divided by the total mass. It's 10 divided by 10, which is 1. So these are the coordinates of the centroid. Okay. So you see, let me just, this is 2.9, right? So the centroid will be at 1 in the y and 2.9. So this is 1, another, this is 1.5. But I need, so over here is 2.5. Over here is like 2, and it's 2.9. So it will be like kind of like here. So here is going to be the centroid, kinda, right? Yeah. So over here is 4 minus 1, 3 minus 0.1, 2.9. Yeah, it's here. Centroid's around here. So this is the center of mass. Okay. Let's keep going. Now that I'm going to talk to you about the theorem of Pappus. The theorem of Pappus just says that, I'm going to show you the image because the image is a lot clearer. Now hold on. Let's just say, I have to do something here. I'm going to erase this thing. I'm going to paste that. Kind of like here. Hold on, I'm going to make this become a circle. Okay. So the theorem of Pappus says that the volume of this torus right here, okay, it's going to be the cross-sectional area because the torus is a circle, right? If one of these discs in here has this shape. One of these discs in here has this shape. It's a circle. So the theorem of Pappus just says that the volume of the torus is going to be, well, it doesn't say that it has to be a torus. It can be, for example, if you have a line, what I'm trying to say is this. Let's just say that you have a line that goes right there, okay, in the middle, and the torus is going around that line. So hold on, the torus going here, that line is going a little bit further, okay, fine, and it keeps going down here. Okay, so the torus going around this line, this axis in here. Well, you're going to find the centroid of the region. In this case, the centroid is right here. Okay, it's the point 2, 0 in 2 of x and 0 in y. And you're going to do 2 pi r. What's going to be r? Is going to be the distance from the centroid to this axis right here times the area of the cross-sectional plane. Okay. So what is it going to be like? It's going to be like volume of the torus, in this case, equals 2 pi r times a. This a, what is a? A equals pi r squared. Well, the cross-sectional area here has a radius of 1. So it's pi 1 squared, which is just pi. Okay? And what is r? The r is the distance from the centroid to the axis, which is 2. So the volume of the torus equals 2 pi times 2 times pi, which equals 4 pi squared. Okay, that's it. Okay. Let me see if I want to keep going. Yeah, just I want to talk about pressure now. It's a little lesson in physics. Okay, I'm gonna show something here to you guys, and then okay. So you got this stuff, okay? What is pressure? Pressure is force divided by area. Okay, so pressure equals force divided by area. The force in this case, because we're talking about the planet Earth, okay, is force of what? It's the force of the column of the fluid. Okay, so you want to talk about pressure now when we're talking about air or water. Now you have to pretend that the fluid is incompressible, because if it's in air, you can compress a lot of the air. If it's a liquid, you're not going to be able to compress it too much. Okay, so we're going to pretend that this is liquid, this is water here. So what is the force? The force is going to be the mass. Oh man, I always got to keep switching the colors. Mass times the gravity. Okay, and then you go like times the height divided by the volume. What is the volume? The volume is the width, the length, the width, and the depth. Okay, now if you take one of these dimensions out, you're gonna have an area. Okay, it's like dimensional analysis. The height is in meters and the volume is in meters squared. Okay, the area it's in meters cubed. The area is in meters squared. So when you have the height divided by the volume, you have meters divided by meters cubed, which equals meters squared. This is the area which is in the denominator, and you have the area here in the denominator. Okay, so this is the same thing as the weight divided by the area, because the height divided by the volume is the area, and the weight in this case is the force. Okay, but is the weight of what? First of all, pressure is going to be the force per area, okay, per unit of area. Doesn't matter what the unit is, but it's going to be the force applied by the fluid per unit area. So here, and the force is always perpendicular, so perpendicular to the area of the object. So here you have a plate, okay, and you have water, okay, all over here you have water, okay. So the pressure is being applied everywhere with a normal in the direction of the normal of the object. So in here it's gonna be all here like that, okay. Underneath the plate will be up. To the right side of the plate will be to the left. Okay, to the front side of the plate right here is going to be towards the front, right? So that is going to be the pressure. Now, there's just one more thing to say. It's the force divided by the area. The force of what? The force of the column of water in here. See that? It's the force of the column of the water weighing on top of that thing, okay, on top of that point of the plate. So it's the mass of what? The mass of water, gravity of the earth. What is this height? The height is the depth. In this case here, the height is 6, okay? This is the height. And divided by, in this case, the volume. And they go like the volume of what? Well, in this case, it's going to be the volume of the object. But when you multiply by the height and divide by the volume, you're dividing by the area. And there's something else that you can do here. This is also equals to mass divided by the volume is the density. Okay, so you have the density times the gravity times the height. The density of what? The density of the water. Okay, the mass of water divided by that volume of water is going to give the density of water. Because it's incompressible, the density is going to be fairly much the same all over. You just consider for these exercises that's going to be the same. The gravity is of the earth, and the height is the height that point of the object is inside the water. For example, what is the pressure that the water exerts on this object if the object were the surface? It will be 0 because the height in here was going to be 0. Okay? So it depends on the depth of the object inside the fluid. Okay. So knowing this, let's try some exercise in here. And then you have something called like the pressure. You can also have the weight density of the liquid per unit volume. Okay? Now pretend I'm gonna get this thing, come over here, okay? Pretend that the volume is gonna be 1. So this formula becomes mgh, right? Mg is the weight. It's the mass times the gravity. So when you have something like this, it'll be the weight density per unit volume. The volume has to be 1. Okay. So yeah, fine. So let's see here. Find the fluid force on a rectangular metal sheet measuring 3 feet by 4 feet that's submerged in 6 feet of water. Okay. And then you go like, because the weight density of water is 62.4 pounds per cubic foot. So the weight density, remember the pressure is going to be the weight density times the height. I'm going to put a little d here just to say that this weight is different from this weight. So it'll be the weight density times the height. Weight density is 62.4 pounds per cubic foot. And the sheet is submerged 6 feet. So times the height times 6 feet. You know, this point of mine here, it looks like it's multiplying. Okay, the point has to go all the way over there. Okay, 62.4 times 6. Okay, so when you make this thing is, well, you can do that here. 4 goes 2, 12, 1, 37, 37. And you gotta put the point in here because there you go. So that'll be the pressure. Pressure is force divided by area, so it's gonna be pounds, okay, per squared feet. That's it. All right. But find the fluid force on a rectangular metal sheet. Now here we go. We found the pressure. We have the pressure 374.4 equals the force divided by the area. What's the area? It's 12 because it's 3 feet by 12 feet, right? That's what it says here. Yeah. So it's 12, okay? And then all you gotta do is multiply this thing. So the force is gonna be equal to 4492.8 pounds. And that's it. Now, on the next video, well, I don't know if I do this on this video. I'm gonna do it on the next one. Because you can see that the force in here, or the pressure, was constant, okay? Now, let's just say that you want to find a force when the pressure is not constant. Then what? Then we can do that thing, right? The derivative, it'll be like, right? We can check all these things. The pressure is going to be force divided by this. So you see, the derivative of the force with respect to the area is going to be equal to the instantaneous pressure, right? Now, if you want to find the whole force, what do? You say dF equals the instantaneous pressure, dA, then you integrate, right? Now, what's going to be dA? dA is going to be the length, because let's just say that you have a sheet that's vertical, but because you can see that the sheet in here is horizontal. So the distance from this point to the surface is the same as the distance from this point, but let's just say that the sheet was like this, right? Now this distance is closer to the surface than this one, okay? And let's just say there's something else in here too. Let's just say that we got a sheet that's like this. Okay. Now you see, you have a function. If you're gonna break this into bars, then you have a function that's gonna tell you where this is, this curve, and this curve in here. Okay. So for example, if this is f of x, or well, in this case it's gonna be f of y, and this is gonna be g of y, then it's f of y minus g of y. It'll give you the length, okay? Now, you do that, and you multiply that by dy, which is an infinitely thin, it's an infinitely thin horizontal bar, okay? For example, you have a bar like this. Hold on. Let me just well, okay. Let's just say that you have a bar like this, okay? And the distance between these two is getting very close, so you're going to have that area, right? Why? Because the area is actually going to be, for example, f of y minus g of y, okay? Which is this length right here, times this thing in here, the distance between these two bars, okay, which is actually going to be the depth of the bar, or the width of a vertical bar. It's not going to be the depth of the bar, it'll be the width of a vertical bar. So you can do like dy. So here you have the area, and you also depend on the height, right? You depend on the height. So what's going to be the height? The height is going to be this point from the surface, okay? It'll just be y, for example. You do like y, whatever. Well, this thing here is dA. So you put this stuff over here, okay, in the place of dA, and integrating that, you're going to get the entire force, okay? Now the pressure, right, depends on the density and the gravity. So given the density and the gravity, you need the height for the pressure on that. The height's going to be y, okay? Because in this place of this p here, you're going to do density times the gravity times the height. The height's just going to be y, which is the distance from this point to the surface. Let's just say that the surface is here, okay? But then you go like, hold on a second. It doesn't matter how thin this bar is, this little area is, okay? I'm gonna exaggerate this space here now like that. Because then you go like, okay, is this y depth from here to the surface gonna be measured here to the surface? Or is it gonna be measured here to the surface? Or is it gonna be measured here to the surface? It doesn't matter, because as these horizontal bars become infinitely thin, they're gonna close in on a single y. As they become infinitely thin, the y between them is just gonna be a point. Okay, that's the limit. So all you gotta do is to multiply this by y. So you do this thing here, you multiply this by y, and d and g, and if you integrate this stuff in here, you're gonna get the force. Okay, so making a mess here, the force is gonna be the integral, okay, of f of y minus g of y. All right, you're gonna multiply this thing by dy, okay, because you want the area of this stuff in here, and what else? And the height, and this, right? And if you do this integral right here with respect to dy, you're gonna get the force, the sum of all forces. So you're gonna get the force exerted by the water over here, and you're going to get the force over here, and you're going to get the force over here and here, blah blah blah, and you add all these forces and you're going to get the entire force, okay, along this thing. But of course the force in here, because it's closer to the surface, is going to be smaller than the force in here, which is deeper considered to the surface here. Okay, so that's the idea for the next video.